Hello, in this video we will be looking at integrals involving exponential and logarithmic functions. First of all, we want to begin with exponential functions. Let's begin by recalling that the derivative d dx of e to the u is equal to e to the u times u prime. All this says is that if you want the derivative of e to the u, it's e to the u, but then you have to chain on the derivative of that exponent. If you have a function and you know its derivative, then you know a corresponding antiderivative. If we start with the function on the right and take an antiderivative, then we should end up with the function on the left. And that's what this notation here says. If you want an indefinite integral with respect to x or an antiderivative with respect to x of this function, well, that's this function here. So how did we get that? We got it by from this thing over here. So we end up with e to the u plus c. Now there's a couple implications of that. One of them is that the antiderivative of e to the x is e to the x plus c. Another one that I want to highlight is if you want an antiderivative of e raised up to some constant a times x with respect to x, then this is always going to be e to the ax over a. Our reasoning here is if you wanted to take the derivative of the thing on the right, the derivative of e to the ax is e to the ax, but then you would chain on an a, and that a that gets chained on reduces with the a that you're dividing by, so then that would just be 1, and that would get you right back here with e to the ax. But let's go ahead and do a couple examples finding antiderivatives that involve e. What's the antiderivative of e to the 3x with respect to x? Well, just following that last pattern, it's got to be e to the 3x, right? The antiderivative of e to the u is always e to the u, but now we have to think about how does this need to be adjusted. If you took the derivative of this, you wouldn't get this thing over here, you would get 3 times that thing over there. So we'll go ahead and divide this by 3 and add on c. All right, this is our answer. How can we check our answer? If you took the derivative of e to the 3x over 3 plus c, this would be e to the 3x times 3. You'd have to chain on the derivative of the exponent. It's still all over 3. The plus c becomes plus 0. Dividing by 3 and multiplying by 3 reduce, so we end up with this thing, which is in fact the thing that you had started with. That's the expression inside of your indefinite integral. All right, next example. If you want the antiderivative of 2000 e to the 0.1x, this would be 2000 e to the 0.1x divided by 0.1. Of course, you do want to take 2000 divided by 0.1. Let's not forget the plus c. Once you do this, 2000 divided by 0.1 would be 20,000 e to the 0.1x plus c. And of course, you can look at this and identify like what would the derivative of this function be. You would take 0.1, multiply it to this, get 2000. E to the ux would stay e to the ux. Derivative of c is 0, so then we see that that checks out. We have successfully found an antiderivative. Last example for these notes. If you want to find the antiderivative of a function that looks like this, well, you'll notice that normally we have e to the to some function, which we currently have. So in this case, because I don't just have like a constant times x as the exponent, I'm going to do a u substitution of the exponent. So let me go ahead and indicate this, maybe here in blue. This is going to be my u function. U is equal to x squared. Then I'll have du dx be equal to 2x. And then the goal here is when we do this u substitution and we compute du dx is we want to solve for dx eventually. So I'm going to multiply both sides by dx. And then divide both sides by 2x. So we find that dx is du over 2x. All right, so this thing here is going to get subbed back into the function, indefinite integral for x e to the u, and then dx becomes du over 2x. At this point, you are really hoping that the x will cancel the x. It might also happen that like 4 reduces 2, 4 divided by 2 is 2, but that's not guaranteed. But you reduce as much as you can. This would be now the indefinite integral of 2e to the u du. So then we could just say this is 2e to the u plus c. And then the final step is let's replace u with what it's equal to. That's 2e to the x squared plus c. This is our final answer. And in fact, it's going to be a lot easier to check your final answer by just taking the derivative of this and make sure that it's equal to whatever this original integrand is. So the thing that's inside the integral. So you might be wondering, when is a u substitution a good idea or a necessary idea when e is involved? Pretty much if the exponent on e is a function itself, that's more complicated than just like a super basic function like a to the x was up there, then we would replace this with u. Now, u substitutions aren't guaranteed to work. In fact, we pretty much rely on the fact that somebody has pre-planned that this x was going to cancel this x. Otherwise, we would have been stuck. But when it's applicable, yeah, we just follow this process of making the exponent equal to u and then doing the u substitution from there. All right, the other type of antiderivative we want to talk about in this video is a logarithmic one. Let's begin with the basic derivative that we know related to logarithms. The derivative of the natural log of x is equal to 1 over x. Now, this is a true statement, so you would think that the antiderivative of 1 over x would be equal to the natural log of x. That's kind of true and kind of not true. So the reason we have a problem with going in the reverse direction here is that the natural log has an implied domain restriction. So you can never put negative numbers or 0 into a natural log function. So if I asked you what the derivative of this is, yes, you tell me it's 1 over x, but the implication is that we never allowed x to be a negative number. Well, if you want to go the other direction, the antiderivative of 1 over x is allowed to be a negative number, so how could we write this function where we do allow x to be negative numbers? Well, what we would have to do is we would have to insert a absolute value around the x, like this. Pretty much only if you are trying to do this antiderivative process. I mean, it is also true that the derivative of the natural log of the absolute value of x is 1 over x. Like, this is a true statement still, because the only thing that really happened here was this getting rid of that domain restriction on the x, that it's not allowed to be negative numbers. It's still not allowed to be 0, of course, but that would be the reason why in these rules you start to see that our answer is the natural log of the absolute value of x rather than just x. Okay, so kind of, it's there for a technicality, but it's something that we are not allowed to forget. Now, this is just a generic derivative that involves x. What if we wanted to generalize it even more and talk about u? So what is the derivative of the natural log of the absolute value of u? Well, that's equal to 1 over u. So that's the derivative of the natural log of something is 1 over the thing. But if this is a function, now you have to chain on the derivative of u. So this would be times u prime. All right. Because this derivative is true, the antiderivative that takes this and turns it into this is also true. So the antiderivative of u to the negative 1 times u prime, or another way of saying that would be the antiderivative of u prime over u is equal to the natural log of the absolute value of u plus c. So taking this, turning it into this. All right, let's go ahead and look at some examples of that. Okay, so what is the indefinite integral, or the antiderivative, of this function right here. At first glance, it's like, wow, that's a quotient. I'm not sure if I know how to do a derivative of a quotient. Sorry, an antiderivative of a quotient. But then you realize, this denominator and the numerator seem to be related. In fact, the numerator seems like maybe it's a derivative of my denominator. All right, well, let's pull out our handy-dandy u substitution. U is going to be equal to x cubed plus 7, and then du dx is going to be equal to 3x squared. So that means du equals 3x squared dx, which means that dx is in fact du over 3x squared. All right, I'm going to take this and I'm going to substitute it back in for dx when I write the next line. So this becomes the indefinite integral of, all right, we have 3x squared. I subbed out the bottom for u, and then I'm subbing in du over 3x squared. Now, in the best possible situation, the nicest possible situation, the 3x squared and the 3x squared will reduce out of the problem. That's not necessary to continue. What's necessary is that the x's disappear. If the 3 here did not match the 3 here, that's fine. You would just reduce them if you could. But if this had been a 7 and a 3, it would be 7/3. So the constants need not reduce, but the x's must reduce. In this example, though, everything has reduced aside from the u's. So now it's indefinite integral 1 over u du. And we would ask ourselves, well, what function gives me 1 over u as its derivative? It's got to be the natural log of the absolute value of x. I'm sorry, I'm used to saying x of u plus c, but we don't want our final answer to be in terms of u. We want it to be in terms of x. So I'll sub that back in. This is natural log of the absolute value of x cubed plus 7 plus c. All right, let's go ahead and do another example. So what is the indefinite integral of 12x cubed over 4x to the 4th plus 1 with respect to x? Now, initially, you look at this and you're like, okay, the numerator is not the derivative of the denominator. It's a little bit disappointing, but it's fine, because what happens is if you took the derivative of the denominator, you would get x cubed, and that does show up in your numerator. So because that relationship is true, we still want to do a u substitution. U is equal to 4x to the 4th plus 1. Du is equal to 16x cubed plus 1. I'm sorry, 16x cubed dx, right? The derivative of 1 is 0. And then when you divide both sides by 16x cubed, you get dx is equal to du over 16x cubed. So this thing is going to get subbed back in for the dx. We have the indefinite integral 12x cubed over, we sub that out for u, then dx becomes du over 16x cubed, and the important thing here, x cubed and x cubed reduce, so now all I have left is this u variable and the corresponding du. Now, if you look at this and you feel pretty good about knowing what the answer is going to be, feel free to go for it. But if you don't, what I might recommend is take this 12 and this 16, bring them out in front as a fraction. So 12 is in the numerator, 16 is in your denominator. 12 over 16, I'll reduce that later. Then you would be left with 1 over u du. And at this point, yeah, let's go ahead and reduce. 12 over 16, we can divide both of those by 4, so you would get 3/4. Then this would be natural log of the absolute value of u plus c. And then, because I'm about to write u in here, I'm actually going to sub in what u is equal to. So this would be 4x to the 4th plus 1. Now, this is technically a correct answer. It's not the most efficient way to write the problem. If you notice that the argument of your logarithm, so 4x to the 4th plus 1, if this thing can never be negative because you raised the variable up to an even exponent and then you only added things afterwards, if you're convinced this can never be negative, you can drop the absolute value symbol here. So in some books, probably most books actually, what they would show is that they would show this is the natural log of 4x to the fourth plus 1 without the absolute values. The absolute values should be used all the time unless you're in a super specific situation like this where the argument can't be negative, and then it's fine to drop them. So if you run into this, they didn't forget the absolute values, they realized they weren't necessary. So this is a more correct answer. All right, last question for these notes. Let's look at an application problem. So what we have is we have a function that's going to give us the rate of vocabulary memorization of an average student in a foreign language course. And then t is the number of continuous hours of studies with a restriction that it has to be greater than 0 but less than or equal to 4. V then is going to be the number of words. And we want to know how many words would the student memorize in 4 hours. Your first instinct might be, what would happen if we put 4 into this function? Well, that would give you the rate of vocabulary memorization. So if we put 4 in here, 4 plus 1 is 5, 30 divided by 5 is 6. So that would be basically a change of 6 words per hour. So 6 words per hour at the 4th hour, but that doesn't tell me how many you've memorized in 4 hours. Okay, to answer that question, we need the original function, so v would be equal to the antiderivative of dv dt, so that's 30 over t plus 1, with respect to t. Now, there's a couple things you can do. In previous sections, what I would have done is I would have rewritten this as 30 times t plus 1 to the negative 1 dt, and maybe this is actually helpful. So what we would then do is the thing that's inside parentheses, we rewrite this as u, so that u is equal to t plus 1. du dt is therefore equal to 1, so du equals dt. Okay, so when we go to do this u substitution, what we have is we're trying to find the antiderivative of 30 u to the negative 1 du, right? Just swapping du in for dt, and we know that u is equal to t plus 1. Okay, so you might think to yourself, why can't I just use a regular antiderivative property? Why can't I add 1 to the exponent, then divide by the new exponent? Well, if you recall, that power rule property only works for values when your exponent is not negative 1. And we see, if you actually try to do it, let me do that up here. If you tried to increment the exponent by 1, you would get 0. Then you would have to divide by the new exponent, which is 0. And you would look at this and be like, I'm not really sure what that means. 30 divided by 0 is not defined. So all of this doesn't work. That would not be defined. But remember that like u to the negative 1 is the same thing as 1 over u. So that's 1 over u du. We know that the antiderivative of that, let me switch back to the regular color. The antiderivative of that, we have the constant out in there, I guess the coefficient, and then it would be natural log of the absolute value of u plus c. In this case, u is equal to t plus 1. Now, they did tell us that t has to be between 0 and 4, so we know that t is positive, so we can drop these absolute value symbols. Let me give myself a tiny bit more room here, and let's do that. So this is 30 natural log of t plus 1. You might ask yourself, well, what would c be equal to? Well, if t is allowed to be 0, like what would the lower limit be? Then that means you would be looking at the natural log of 1. The natural log of 1 is defined to be 0, so 30 times 0 would be 0. So c is the basically how many words will you learn for 0 effort. And it would make a lot of sense to realize in the context of this word problem, c would be equal to 0. Because if you put 0 hours of study in, and then all of that becomes 0, then you aren't going to learn any new words. So this is our function. We don't have a constant of integration. Let me actually write v is equal to this. And now that we know what v is equal to, we can go ahead and solve our problem. Okay, let me give ourselves a little bit more space, change to a color that's readable in the black space down here. I'm sorry, I should have written v is equal to that. There we go. All right, so because they want to know how many words would the student memorize in 4 hours, what is v of 4? That would be 30 times the natural log of 4 plus 1. So this would be 30 times the natural log of 5. All right, let's put this in a calculator. I'm getting 48.28. And you should realize that this is words that are being memorized, so that would have to be rounded to the nearest whole number. All right, so we'll round this to 48 words. All right, that's going to conclude the notes for this video. Hopefully that is helpful as you think about antiderivatives of exponential functions and logarithmic functions.